thank you for everyone who is here to be here. And let's restart with the...
Okay, thank you. Thank you for coming this early morning. Although I guess for Brazil, this is not very early morning. Yeah, so it's late morning. Okay, so today there's the last lecture. And it is just, let me just continue what we, from the point we stopped last time. Yeah, remember we derived this gap equation. Let me write it like this, minus g. Last time it was modulus g, but we know g is negative, so minus g is just a modulus. Yeah? And then we have this integral dp over 2 pi h bar cube. And then we have tangent, okay, sorry, tangent. Is it for you normal notation? Because it varies very much from country to country. It's standard form, yeah? Okay, EP divided by 2t divided by 2EP, where EP is just square root of psi p squared plus delta squared. And I told you that this equation actually suffers from what scientifically called ultraviolet divergence. Yeah? If momenta goes to infinity, your tangent goes to 1, and here you have just p squared, and d3p over p squared diverges linearly with the upper cutoff. Yeah? And of course, the reason for this, we know the reason for this, we can understand. The reason for this is when we replace the true Fourier component of the potential with the constant. Yeah? So in field theories, it's really a point-like interaction, at least assumed between the elementary particles, point-like. But between atoms, that's not the case. The atomic interaction has a particular range. Yeah, so this would definitely violate, be wrong approximation for momenta q. So this is good for q only of the order of inverse interaction radius. Yeah? Inside this radius, the potential has internal structure, so this dependence on q will show up wildly, and we just throw it away. Yeah? So, and this is wrong, of course. Yeah? But large momenta means that two particles come close, very close, so this is two-particle problem. Yeah? So somehow we must be able to cue this problem coming back to the Schrödinger equation, to the lectures of York. Yeah? But first step, what we do, let me introduce here just to make sense of this integral, right? Because make no sense, infinity. Yeah. Introduce the upper cutoff lambda, which I assume to be lambda is something of the order h bar over r0, the size of my interaction. Yeah? And then I will show you now how to get rid of this upper cutoff. In field theory, this is really upper cutoff. But in here, it is how one can get rid of internal details of your interaction. Yeah? That has a bit different meaning, although mathematically it looks very much the same. Yeah? To do this, as I said, we have to go back to the two-body Schrödinger equation. Yeah? Because two particles close to each other, they don't care what's going on around. It's just two particles. Yeah? And then I will need the quantity which is called off-shell scattering amplitude. This is kind of very theoretical quantity. So it depends on energy and two momenta, incoming and outgoing. Yeah? And particularly important here, why it's called off-shell, yeah, is that, first of all, the modulus of these momenta not necessarily equal. Yeah, we know from the elastic collision they has to be equal. They have to be equal, huh? Because, yeah. And moreover, they are not equal to square root of m energy. Very often people write here z, just to. Why m and not 2m? Yeah, because you know from the collisional lecture on collisions, that's here 2 effective mass times m. Yeah? When two-particle collision of two particles is equivalent to scattering of a single particle with a reduced mass on some potential. And reduced mass for two identical particles is Mu is m over 2. Yeah, that's why here m. Yeah, and not equal to this one. Yeah. This quantity contains all information about the system, scattering, as I will show how, bound states, etc., etc. Yeah. And this quantity is defined, so just to make a connection, if I make on shell, this is also a very scientific term that comes from field theory. On shell in this case means that the P equals to P prime, on shell means physically, and equals to ME, when we really describe the collisions of particles, elastic collisions. So this is elastic collisions. Then, for these things, this gamma E P prime goes into 4 pi h bar squared over m times the scattering amplitude, f p prime. So this is our scattering amplitude. Which was discussed in the lectures of IQOQI. And of course, if we now set E goes to 0, so that means E goes to 0 and modulus also goes to 0, then of course these things gamma will go, because we know this goes to the scattering length, right? We have a short range potential, so it goes to the 4 pi h bar squared over m times scattering length. So this is all nice, but how it is defined? It is defined in the solution of the following integral equation. Gamma E P prime equals Fourier component of the potential P minus P prime plus integral dq over 2 pi h bar cube. And then we have V tilde P minus Q 1 over E minus Q squared over M plus I0 gamma E gamma on E Q P prime. So this is this integral equation. It has a very simple physical interpretation. So let me put it here on this part of the blackboard, just not to erase immediately. So as I said, we describe collisions between particles. Remember this nice representation for this interaction Hamiltonian between particles. So particles go and this sort of representation for this interaction. So this, here we have some particle P, here we have minus P in this case, because momenta, and here we have P prime, and here we have minus P prime, and here we have P minus P prime, tilde. That was our representation. So, but this is, of course, the first part. It's a lowest order scattering. This is the first term, this V. But then, of course, particle can undergo collision twice. So this always P, this is P prime, this is Q then, and okay, P1 or whatever. So this minus P prime. But they can undergo 3 times, etc. So this is, but then it's typically these sort of things. Let me call all this by gamma. But now, what this equation means, it's a very simple construction. Let me isolate the first one. And in all the rest, the first line to the left. And then you see what comes to the right is exactly the same infinite sum. Yeah? The same infinite sum. And therefore, I can represent it like this. So here's V tilde, this is gamma. And if you know the rules, how to identify these lines with some analytical expression, then you add up exactly in this equation. Yeah? So this is what is called also, if I consider particles here on shell, yeah, so I just put these things for F in here, I get something in here, and then what you recognize, this integral equation for scattering that gives you the Born expression. Yeah? Because forget for a moment, if you forget this part, yeah, because it's higher order. Yeah? V starts with, gamma starts with V, and this term is definitely V squared at least. Yeah? So if I just limit myself to this part and put it this expression for my E in terms of F on shell, then you immediately recognize the Born approximation for scattering amplitude. It's just up to some this coefficient inverse m over whatever times the Fourier component. It's Born approximation. So this equation, yeah, but Offshell, it contains much more information, bound states, etc., etc. Yeah? So now, but let's do, and this is exact equation, yes?
In this case, the wavy lines represent phonons?
Weak lines, wavy lines represents the interaction, and solid lines, it's a particle propagation. So it in the end, it gives you this part.
But is it the wavy line related to some effective particle or something?
No. Wavy line is just it's just graphical representation for this interaction. Okay. Yeah? Remember this part. We have V on Q and AP2 P1 plus Q dagger AP2 minus Q dagger AP2 AP1. It's this one.
Yeah. Like in Q theory?
Yes. It would be the propagator for the. No, here it's not. It's just this wavy line, this Fourier component of the interaction. Yeah. So now let's have a look at this equation and make the same approximation. Yeah, let's make the same approximation. What do we get? We get gamma on E PP prime equals now G, right, plus this integral goes away. Yeah, so not it goes away, but what am I saying? G goes out to the integral, yeah, because V tilde is G. Then you have an integral dq over 2 pi h bar cube, and then you have 1 over E minus Q squared over M plus I0. And this I0 that gives you this scattering boundary condition, outgoing waves. Yeah, so this is sort of mathematical subtleties. And now gamma E, and E gamma at E, Q, and P prime. So first of all, we now see that there is no dependence on P, yeah? And by symmetrical consideration, you would also find, okay, you can do the same trick with the most rest line, yeah? Then the gamma and V will replace the place, yeah? So there is no P dependence, and actually, for the same reason, you can argue no P prime dependence. So it's similar story. Yeah? And of course, we know that here we have to put again lambda. Yeah? So if there is no dependence, so therefore, actually gamma in this case is only a function of the energy. Yeah? And nothing else. And this function of an energy satisfies this equation So you see, you get the same divergence as large Q. Yeah? Let me now set E to 0. This is a bit what I do is hand waving. Yeah? Then, of course, I know that gamma and E goes to 0 is just 4 pi h bar squared over m times scattering amplitude. Well, let me call it, for simplicity, gamma 0, just to make notation a bit shorter. Yeah? So then, for gamma 0, I get the following. Gamma 0 is G plus, now because E is 0, I get a minus G gamma 0 integral dq over 2 pi h bar cube. And then here we'll have m over q squared. Yeah. So now, how can I combine this one and this one to get rid of lambda? Yeah. So let's do the following. Let's here divide both sides by G gamma 0. Yeah. So then here I will get 1 over G equals 1 over gamma 0 minus this integral. And now the gap equation that I have, let me divide by G. Yeah? From the gap equation, I will get 1 over G equals minus integral and then this tangent yeah. So now we have this 1 over G, let's take them equal, yeah, and see what happens. Yeah. So now we have, probably I should, easiest way is just, should I subtract? Yeah, probably. Okay, so then we have minus lambda dq 2 pi h bar cube, and then this tangent EP over 2t 2EP equals, and now we have 1 over gamma 0 minus integral dq 2 pi h bar cube, and then m over q squared. Yeah, so now I can combine the two integrals. Yeah, so what I get here and multiply by minus, I will get minus 1 over gamma 0. Remember, gamma 0 is negative, so it's positive quantity, equals integral dq over 2 pi h bar cube. And now we have a difference of these things, tangent EP 2t divided by 2EP minus m over, okay, sorry, p should here, I replace p with q, yeah, just to have q with p, yeah, because it's integration variable. So you get like this. And now in this integral, asymptotic of these things for large p is also m over p squared, because it's 2. Yeah? So it cancels. If I look at this expression at a large momenta, it starts with 1 over p to the 4th, which is convergent, yeah, for large p. d3p divided by p to the 4th converges. So therefore here, you can set lambda to infinity. So that means all this information about small distance behavior of your potential, you now observe going from G into the scattering length. So gamma 0 is your scattering length. That's it. So now we have a well-defined expressions that should define for us delta as a function of whatever temperature, yeah, for our BCS model. Yeah? And let me now, I don't want to spend time analyzing these things. I just give you the result. Okay, most of these which you already know. Okay, so first of all, delta non-zero appears only for T smaller than Tc, smaller than some critical temperature. Otherwise, we always have solution delta zero. Above Tc, solution delta zero. Below Tc, we have this solution. I won't do these calculations, but you can check that this state with delta non-zero has lower energy than the normal state. Yeah? So it is not you get some fictitious state with a higher energy, but indeed, if you compare the energy of this state with delta non-zero and a normal state with delta zero, this state has a low energy. Yeah? So we get here a lower energy state. So indeed, then this would be the ground state. Yeah? So what is this Tc? Tc, let me write here BCS. We are in the BCS model. Yeah? We consider only scattering of particles with the opposite momenta, only them. Remember our Hamiltonian. So if you do these calculations, you get this number, e to the gamma over pi. This you can find in the book 8, e to the minus 2, epsilon Fermi, e to the minus 1 over f. And remember, this f is our 2 modulus A P Fermi over pi h bar. We do get exponentially small Tc. Yeah, as in, remember, Cooper problem. Clear Tc should be of the order of this pairing gap. That's what we get. Yeah? And delta has, of course, some temperature dependence. So, and it looks like this. Let me write here. Delta as a function of temperature. It all comes from the solution of this equation. Analytically, you can work out region of close to 0, yeah, and close to Tc. Yeah, because in one case, you just ignore the tangent. Yeah, in the second case, delta is very small. You can linearize, cancel, etc. So this is Tc. So it behaves so let me remove this mp squared. So it started at some value delta 0, then it goes like this. This is behavior delta as a function of t. This delta 0 is always related to Tc by these, gamma is an Euler constant. This is pi e to the minus gamma Tc. This is standard, this mean field relation between the pairing gap at 0 temperature. So you see it's also exponentially, so this factor will simply disappear, and then what you get? Delta naught would be 8 e to the minus 2 epsilon Fermi, etc. So this is the typical expression, so exponentially small. So how it behaves here, so here for t close to Tc, let me write in this area, delta on t is just, okay, so there is some nice coefficient. Okay, let me write it, 5 pi squared. Okay, no, I won't write this. Zeta functions, etc. So it's just 306, and then Tc. Yeah, we need a scale, energy scale or temperature scale, k Boltzmann is 1, and then we have square root of 1 minus t over Tc. So it's typical mean field behavior. So here, in this area, it is delta on t is this delta 0, and then you have 1 minus square root of 2 pi t divided by delta 0 e to the minus delta 0 divided by t. So it's exponentially small, exponentially deviation. So here it's practically horizontal and then square root. Yeah. So this delta, for those of you who knows the second order phase transition, this is second order phase transition. Going into this superfluid state is a second order phase transition. Where delta plays the role of the order parameter. Remember that was G, and then we have psi minus R, psi plus R. This is our order parameter that appears below Tc. Yeah? And this order parameter clearly breaks, second order, you always break some continuous symmetry. Yeah? And here it's clear the symmetry you break is the gauge symmetry. So this order parameter breaks the gauge symmetry, U1 symmetry, which is psi sigma of R goes into e to the I phi psi sigma of R. You change the phase of your field operator, and clearly because you have here psi psi, this order parameter changes. So when this appears, this symmetry is spontaneously broken. No? Then I'm not going to discuss now, but later on, and if I forget, please remind me, two things with respect to this statement that is a second order phase transition I want to discuss. First of all, we know that second order transition always relates with fluctuations. Yeah? It is when the fluctuations becomes very important. So, but at the moment it's all mean field. So the question is fluctuations. And the second, we know if you break continuum symmetry, for the Noether theorem, we must get Goldstone mode. Zero energy mode, Goldstone mode. So please remind me at some point, because now I still want to discuss a bit several things related to first Tc and second to the properties of this state.
I have a question.
Yes?
Is the critical exponents of this transition are
Mean field.
mean field?
Mean
so
field.
It's not correct in the sense that.
Just wait, please. So the question is, so of course here there must be some fluctuation regions. Yeah. The answer to your question, just to, is that it's extremely narrow.
Extreme narrow.
You cannot see it in experiments. You cannot see it in experiments with at least weak coupling semiconductors.
Okay.
So you cannot.
So the mean fields works very well in the experiment.
Perfect.
Okay.
Perfect. Yeah. Perfect. Works perfect for these superconductors.
Okay.
Mm-hmm. So two things. First things I want to discuss. I especially put here BCS. Yeah. Remember, we just select only particular collisions. But in a gas, there are many other collisions. So what happens with them? First of all, you have to understand where the other collisions come. So what we consider is this one only, yeah, plus minus. Yeah, that was these collisions where we have here P, we have here minus P, we have here again plus P prime, and here we have minus P prime minus. Yeah, that was our collisions that we take into account in our BCS model. But of course you can think, well, how can I make a next order? Yeah, what happens? Because in a sense, anyway, we can see the Cooper pairing, yeah, with opposite momenta. In lowest order, that's the only thing we need. Yeah, zero total momenta, zero total momenta. When you go to second order, then they come, and this the picture looks like this. So this, let's say, P plus, and now we have P prime plus, and the lower one behaves like this. I will explain. So this is, oh, sorry, this is P prime, right? So this is minus P prime minus, and here is minus P minus, and it's all minus line. So what happens? So we have two incoming particles, but instead of like here, they scatter on each other. First, what happens that these plus particles interact with the minus Fermi C and create particle and hole excitation. Intermediate particle and hole excitation. So now here you have plus particles that scatters from here, and you have incoming minus particles that at the moment don't scatter, and particle and hole excitation in a minus component fermionic system. And then second interaction with the plus annihilates, so they recombine the incoming particles with this hole, yeah, and in the end this comes out. So you have plus minus here and plus minus here. But in the middle, you have definitely particles with non-zero total, pairs with non-zero total momentum. You can also think, reverse the picture, and you can write it like this. So the same happens with the plus. Yeah? And this is minus everywhere, and this is everywhere plus. Now, if you take these things into account, this is F, right? This is roughly F squared in dimensional units because of second order. Yeah? So why should I take into account this second order? Yeah? Because I think it's small, I can neglect them. It's because of this strange behavior. Because if I write here F and here I write alpha F squared with alpha some coefficient. Yeah? So if you look at the function 1 over F plus alpha F squared, because this should come in denominator, then it is 1 over F, 1 plus alpha F. This is small, you expand, you get 1 over F approximately, 1 minus alpha F plus higher order, and then you see what happens. You get 1 over F plus minus alpha, F independent, plus terms which are small compared to F. But this is of order unity. This of order unity affects this coefficient. So therefore, one has to take them into account in order to get the critical temperature in a Fermi gas, not in a BCS model, but in a Fermi gas. And clever people, Garkov and Milik-Barkhudarov, did it first, and one of the papers that I recommended, that was a technical paper. I completely understand that you don't want to look at it. Yes, there is this more simplified version of this. So I give you the answer for the critical temperature. So here, let me write this coefficient, just to compare, is 0.61. If you put all these numbers, and 0.61. So the answer for the gas is, e to the gamma over pi, that remains the same, and now comes 2 over e to the power 7 over 3. And then comes epsilon Fermi, e to the minus 1 over f. So you see modification, yeah, some modification. So these things is 0.28. So these higher order collisions that you ignore in the BCS model, they actually reduce the critical temperature by a factor of 2. Bad sign for the experiments, but that's life. Yeah. So let me now say a few words again about this structure of this BCS state. For this, let me recover this excitation energy. Yeah? So that was P, that was P Fermi, that was EP, this is 0, and I remind you if it's epsilon Fermi, that was the dashed line, was the ideal gas or weakly interacting gas, depending whether you use M or M star. Yeah, and now the BCS pairing reduces, gives you, if I write with this color, let me check whether you see it, because otherwise I can. You get it like this. Do you see it on the back? Yes or no? Yes, good. And this was our delta. The question is, what is the momentum interval, delta P, around P Fermi, where this small gap, exponentially small gap, disturb the free particle excitation dispersion? Yeah? For free particles, I remind you, EP, let me put here 0, was close to these points, P for P close to P Fermi, so clear that's the only region which is of interest for us. That was V Fermi times modulus P minus P Fermi. So in this case, we have here a bit more complicated form, which is somewhere. Okay. In our case, EP, if I write the same for P close to P Fermi, yeah, that was delta squared plus Xi squared. This is exactly Xi, so plus V Fermi squared P minus P Fermi squared. That's the dispersion close to P Fermi. It's this curve here. So clear that this delta P, where these two expressions differs, yeah, is delta P is given by of the order of when this term is comparable to this one. Yeah? So therefore, this delta P is delta divided by V Fermi. It's this area where the two dispersion for free gas and paired gas differs. Yeah? Because then this term dominates, and then you recover this one. Yeah? It's only in these regions. But now if you remember, well, you of course remember, yeah, the uncertainty principle, these things translates into some length, yeah, Xi, which is H bar over delta P, and this is H bar V Fermi over delta. And this length called correlation length. We will see its meaning in a minute, but let me first estimate order of magnitude of this quantity. Yeah? So let me write here because this is inconvenient. They should make this movable, like what we have. Yeah. So let's estimate Xi. Yeah? Xi is H bar V Fermi over delta. Let me do the following. H bar over P Fermi times P Fermi V Fermi divided by delta. Yeah? So it is of the order. So this one is double Fermi energy. Yeah? P Fermi V Fermi, it's twice Fermi energy, but forget about 2. Yeah? So that's why it's order of H bar over PF epsilon Fermi over delta. What is H bar over PF? Remember, PF was related to the density of power 1/3. So PF is inverse interparticle separation. Yeah? So that means here I have interparticle separation n to the power minus 1/3. This is interparticle separation. So average distance between particle and your gas. But then you multiply it with the exponentially large number. Yeah? And then you get which is very much larger than n to the power minus 1/3. So this correlation length, it's much, much larger than average interparticle separation. So we cannot talk about bound states for sure, because what are the bound states if they overlap so strongly? Yeah, that's why these Cooper pairs, it's a, you better say, correlated states of two fermions. Yeah? Bound states, it's not definitely, yeah, but it's correlated states, and this, as I will show you in a second, this is exactly the size of this correlation. Beyond this distance, correlation decays exponentially. Yeah, and yeah, but this is actually also this condition that's much larger actually justifies for you very much mean field, because this such a huge volume that all the possible fluctuations averaged out. And you have a very nice mean field description. So this BCS is a perfect example for the mean field approach to the second order phase transition. Yeah? So to see more precisely what is the size of this, why I call this correlation length, yeah, I just present the results for one of the correlation function, which is anomalous correlation function. So let me calculate, how should I call it? C R1, R minus R2, or R minus R prime, which is this one. I average over the new ground state, yeah, and then psi minus of R1, psi plus R2. So if you put in the expressions for this field in terms of alpha operators, remember, if R are the same, R1 is R2 are the same, that's up to G, our order parameter. So we calculated this when we derived the gap equation. Yeah? So if R1 equals R2, if I multiply with G, that was my delta. Yeah? So these things, if you work it out at zero temperature, gives you sum over P, probably 1 over volume. And then you have UP, VP, e to the I over H bar, and then you will have P, and I guess would be R1 minus R2, because you need here conjugate field. Yeah, you get it like this. Yeah. For the gap equation, that was absent. Yeah? And this, I remind you, was delta over 2 EP. So you can work with this integral and calculate it. So I give you the answer. So if I consider distances R1 minus R2 to be larger or comparable with this psi, yeah, then what you get, and psi here, I can write psi 0 if you like. Psi 0 is H bar V Fermi over delta 0, because 0 temperature, I see it here. Yeah, delta 0. So then what you get is the following. You get V Fermi delta 0, and then you get sinus K Fermi R divided by K Fermi R. Then you get square root of pi over, okay, here you have some McDonald's function, but I just use the asymptotics. Okay, let me write McDonald's function. Because it's, so K0 of R1 minus R2 divided by psi 0. And asymptotics on this function, when R1 minus R2 over psi becomes much larger than 1, yeah, if you want to see the, this function behaves like square root of pi over 2 psi over R1 minus R2, and now comes exponent, e to the minus R1 minus R2 divided by psi, 0, 0. So you see these correlations decay exponentially at large distances, but typical size of this correlation is psi 0. So inside this psi, or psi 0, they are non-zero, and then they start decay exponentially. So this is indeed the correlated states of two fermions of opposite type and opposite momentum. Yeah?
That equation for 1 over gamma 0, that means that the scattering length goes to infinity, right?
No. The scattering length is actually, we can see the weak coupling regime. Yeah, so therefore scattering length is actually small. K Fermi R is small. So you want to ask me what happens if I start increase A, or what? So this 1 over gamma 0, or minus, it is, what it is? It is m over 4 pi h bar squared 1 over modulus A. That's what it is. Yeah?
But the equation above goes to 0, right?
Why?
The integral, when you said like when you take the cutoff to infinity.
No. It's only this bracket goes to 0, so it approaches to 0, 1 over p to the 4th at large p. Close to p Fermi, that's the whole, where the whole physics is, they are clearly different. Yeah, so here's m over p squared, so here you have something divided, so it's clearly different. Yeah? So actually this integral, most of this integral comes from the region close to p Fermi, the most interesting logarithmic part, close to p Fermi. Mm-hmm.
My question was like, how does the scattering length influence like the correlation?
Oh, it goes through it's through, so here delta, and psi naught is also defined by delta, and delta naught is roughly Tc, and in Tc you have it here. Yeah. F is our, yeah. So I have to multiply by the density of states that comes from this integral. Yeah, so here, and then I get F. Yeah, so it's in here. The scattering length sits here. And therefore in delta 0 and in psi. So it's a prefactor and the psi, they depend on your scattering length. Yes, the next, what I want to discuss very briefly is probably here. At some point, we have this in lectures of Michel Brun. We have these superconducting mirrors, etc. So that the system has a gap has actually a remarkable or strong consequences for the interaction for the metal type with light. Yeah? So let me calculate. We calculated many times density of states of particles, right? So now let me calculate density of states for excitations. So what it means, I want to, let me call it on epsilon, and excitations means I always have epsilon positive or 0, yeah, because it's excitations. And then I just sum over, I have a uniform space, so I just integrate over momenta with a delta function epsilon minus my excitation energy. So I just fix some excitation energy. This integral tells me how many excitations with different momenta, in our case, I have. And of course, when I have a two-component Fermi gas, let me multiply by 2. Yeah, this is sigma equals plus or minus, yeah? Because we have, for plus and for minus, we have the same, yeah? So that's why I multiply by 2. So now this quantity for the ideal Fermi gas, let me call it nu 0, yeah, it is when I put, it's 2 integral dp, and then I have delta epsilon minus, and now you remember this psi p. Yeah, that was our excitation in ideal Fermi gas. So therefore, what you get here, remember how we did integral. Yeah, we did it already. We would be interesting in epsilon much smaller, and let me consider the interesting case, epsilon much smaller than epsilon Fermi. yeah, such that I'm interested only near the Fermi surface, yeah, then of course I will get dp. I can replace with 4 pi, which my angular integral, right? Because this is only momentum. Then I have p squared dp, and the next, what I will do, I will make p times m d psi, p. We did it already a couple of times. Yeah? And then this I replace with p Fermi. This is all this based on this one, the last one. This is exact, up to here exact, and now here I use that epsilon much less than epsilon Fermi, so my p are close to p Fermi. So now if you do this integral, and then you will recognize, because this has two solutions, psi equals minus epsilon and epsilon, yeah? So you have to sum up over all zeros of the delta function. I get an extra 2. So what I get, 4 new Fermi. And new Fermi, again, is mp Fermi over 2 pi squared h bar cube. Density of states of particles on the Fermi surface. So here I have factor of 2 for the reason particle whole, and I have 2 components. So it's a factor of 2. So now if I calculate for the paired gas, I have to perform a bit more complicated integral, because now I have minus square root of psi p squared plus delta squared. But still you can find the 2 zeros, yeah, of the delta function, and you know how it works with the delta function. You have to divide by the modulus of the derivative at 0. Yeah, so let me save time. So I'd give you simply the answer. First of all, you see that you can have 0 here only when epsilon are larger or equal than delta. Because when epsilon is below delta, because these things is always larger than delta, huh? It lives above the gap. So if excitation energy lies within the gap, there is no excitation there. So you start with delta, and the answer would be 4 new Fermi. Then you have epsilon divided by square root of epsilon squared minus delta squared. Or you can put here real part if you want, just to make it, or real part everywhere. So you see, first of all, epsilon has to be larger than delta. Yeah, so here, epsilon larger than delta. But then you have a singularity when epsilon start approaching delta. So the function, a picture looks like this. Picture looks like this. So if I plot here epsilon, 0, this is my delta, this is my nu on epsilon. Of course, asymptotically, when epsilon becomes larger than delta, yeah, this approach to 4 new Fermi. Yeah, that's what you would have in ideal gas. But now you have a structure like this. So here is 0. And all what was here for the ideal gas is pushed in this peak, 1 over square root of peak. So this behaves like 1 over square root of epsilon minus delta. So here you have a gap, 0, and here you have a peak. And that's what people, when they measure this high TC material, if they measure the density of states by excitation, by some scattering or whatever, so angular resolved spectroscopy up. Okay. So they really see, if they even above TC, they see here some small background, and then they have here, not of course infinite peaks, but some peaks, and they call it pseudo gap. Yeah. So this is typical structure for the density of state, of excitation, sorry, for these paired states. So here, system is transparent for the fields that create single particle excitations, like electromagnetic field. Yeah? If you have something that could create collective modes, which I now will discuss, briefly, then of course you get some response, but if your field like transverse electromagnetic field coupled to single particle excitations, for these frequencies, within the range of 2 delta, because you have to create 2 excitations particle, the material is transparent. Simply goes through without any kind of absorption. Okay, so now let me come back in here to this one. Fluctuations. Indeed, no, I erase it, right? So here, if we write here delta as a function of t, that's what we have, Tc, 0. So for the second order phase transition, so here there must be a critical region. So this is critical region, where fluctuations normally are important. Yeah? You cannot simply based on a mean field. Yeah? But what is the size? So you can estimate the size, temperature size of this critical region where fluctuations are important. And if you do these fluctuations, what you call is Ginzburg-Levaniuk criterion, where the fluctuations can be ignored or has to be considered in the opposite case, if you estimate the size of this region. So what you do, you just, let's say, take specific heat. That's the most probably easier calculations. And you calculate corrections due to the fluctuations to the specific heat. And see when these corrections becomes of the order of the mean field results. And then you find out that this region is, of course, natural scale is Tc, but then comes a very positive surprise. T over epsilon Fermi to the 4th power. For weakly coupled superconductors, like in metal, when T over epsilon Fermi is at most 10 to the minus 2, this is 10 to the minus 8. So forget it, this is 0. You will never reach this region in a weakly coupled superconductors. Of course, with cold atoms, we have a privilege because we have Feshbach resonance. We can tune our system to the region where this becomes of the same order. Yeah, we really can probe this region, and then, yeah, okay, comes sort of universality ideas, because if you go to this region, you set A to infinity. That doesn't mean that actually A, okay, A is a funny thing. It simply means that your scattering is unitary. Your scattering amplitude is 1 over this cross-section 1 over k squared. Yeah, unitary limit for scattering. Yeah, so and k is typically k Fermi. Yeah, so because it's the energy of the colliding particle on the Fermi surface. So you don't get actually here 0, but people use this simple expression to describe the crossover from BCS to BC. Just okay. Yeah, and the second question. So this for weakly coupled pairing mean field works perfectly. This is the question number 1. The question number 2, Goldstone mode. They are related to the fluctuations on delta. These are a phase fluctuations of delta. So that means if I consider delta R and T of the form delta, let's say 0 temperature, because I put here delta 0, e to the I phi, which is R and T dependent. Then you can, in principle, derive the equation for these 5 fluctuations, but this is not so simple like in a Bose-Einstein condensation, because the Gross-Pitaevsky is a small fluctuation and the Gross-Pitaevsky equation with the order parameter. Yeah, because the Gross-Pitaevsky, just to take the average already in the initial Hamiltonian. Here, to get delta, you have to come through this painful self-consistency condition. Remember, we assume delta, we find U and V, and then we put them back to the gap equation to find the consistent equation of delta. So something like this you have to do here, yeah, or you have to use the green function technique. which is also requires some knowledge and experience. And this collective mode appears as a pole of the two particle scattering amplitude in some channel. You will recognize them. Yeah. And indeed, then collective mode, it's called Boголюбов-Anderson, that is PW, famous Anderson, sound. And they indeed appears like a sound. Yeah? So omega is just C times K, yeah, that's a sound dispersion relation. And C in this case, V Fermi over square root of 3. Almost. Of course, there are interaction corrections to this value, but it's like what you have naively in the ideal gas thermodynamical sound. I showed you that would be this answer for the sound wave. Yeah? So here, yeah. So now if we look all these, remember we discussed this as a feature of this normal Fermi gas or ideal Fermi gas linear dependence of specific heat. Of course, it's also instructive to look how specific heat looks here. Yeah, and what you find out, I'm not presenting much detail of the derivation. Yeah, I just give you the final answer. So here, so if I look at the specific heat as a function of temperature, yeah, in the ideal gas, you will have it linear behavior. Yeah, remember? Yeah, that was a trademark of Fermi surface. So now these things, of course, goes after TC. After TC, we have no pairing. We have a linear specific heat. But below, you can guess what would be a behavior. We have a gap. So it will be exponential suppression of specific heat for single particle excitation. What you get here looks like this. And here there is a jump. Well, you can calculate all these jumps. It's important that here, specific heat behaves e to the minus delta over T. Of course, delta on T over T. It's activation. Yeah? Activation mechanism. Yes. So now this is how it behaves. And maybe now, yeah, you can maybe ask me, we discuss things, what are the crucial for this pairing, what we discuss. First of all, we need two components, yeah, because we have short range interaction. So S wave, we want S wave. And I started with always equal concentration and equal mass. Yeah? So you can ask me, what is, if I start, okay, I still have the two components, but if I start violating the other two conditions? Either I have different concentration, or I have a different mass, or I have both different. So the most crucial part for BCS pairing is a different concentration. Because what you must have for a good BCS pairing is that the Fermi momenta of both components are close, are the same. Because the delta, the pairing has some energetical scale delta. So if the difference between Fermi C's in energy would be of the order or larger than delta, clearly pairing is impossible. So therefore, in order to have this type of pairing, S-wave pairing, you need a very highly balanced densities. Different mass is not that important. You replace just a mass with the effective mass. If they have same concentration, it's a trivial modification of the formulas. But having equal concentration is important. Because if you have delta epsilon Fermi, let's say, let me call it plus minus epsilon Fermi minus, becomes larger of the order delta, there is no pairing. On the way, this is called Klockstone limit. Yeah. In superconductors, that is related upon the applying magnetic field, yeah, which has polarized and making up and down unbalanced. Yeah. In the cold gases, it's just a number of particles. On the way, there is a very interesting phase, which is called FFLO phase, which is, almost already seen in the dipole systems, but where the order parameter is intrinsically periodic in space. So it turns out that instead, when you have two different Fermi surface, it's not like this. The Fermi surface deform themselves to come close at some point. Of course, you lose kinetic energy, yeah, because you take particles to high. But at the same time, you make them closer, you win in the pairing energy. Yeah, and because it happens not everywhere, but in some directions, you have periodic dependence in space. So this is F, F, L, O, or L, O, F, F. Yeah, full differential Larkin-Ovchinnikov or Larkin-Ovchinnikov, full differential. It depends whether you like FFLO or you like LOF. Yeah? So, yeah. So, to finish this discussion, I just make a comparable table, like what I did. Ideal gas, repulsive gas, and then I briefly tell you two stories about what happens in a not short-range interacting gas. So let me make a comparative table. Normal gas, that means repulsive gas, or ideal gas in a kind of a simplest version, versus superfluid, this paired system. Yeah? So let's now compare. This is normal. That means no pairing. And this is paired or superfluid. So again, we start single particle excitations. Yeah? Oh, probably no. Probably let's start particle distribution. N, P, P. So here we know ideal gas as a step function. Let's say 0 temperature. 1 P Fermi. And in either we have a step function ideal gas, or you have discontinuity. Yeah? Generically, you have discontinuity. So it discontinues at 0 temperature. Yeah? So here, remember it was Vp squared. It is continuous. And here it's just 1/2. Yeah? If I go to single particle excitations, then here I have these gapless excitations. And here I have gapped. Specific heat, I just draw here. I can say specific heat. So here is proportional to temperature. So here proportional to activating mechanism over T. But of course, you have here also contribution. The dominant would be contribution of the collective mode. Yeah? Both, so here they are T cube. Because it's a phonon-like thing. Then let me continue here. Now number 4, collective modes. So here we have 0 sound. And velocity u is approximately v Fermi plus some exponentially small addition. So here we have Bogolyubov-Anderson sound, where C is V Fermi over square root of 3. Yeah? So you have this comparison. In the cold atoms, you can actually go through the different regimes, and then you really can see this. It's also discrete spectrum, but you can see the difference. Whether I have something, let me check. Ah, yes, density of states, of course. Excitations, density of states. So here, okay, P of the order P Fermi. Yeah, of course, that's the most interesting part. So here we have nu f, constant. And here we have this behavior. So here we have gap. So therefore, materials are not sensitive to excitations that create single particle excitation, to some perturbation that creates single particle excitation. So this is just a basic things to compare. So I skip all this vortex formation, etc., which are very similar to what you have in the BEC, because you have the same order parameter, U1 violation symmetry. And let me spend some time to tell you two stories about the pairing. So we looked at the pairing with a short-range potential. So now, because I contact Jora, who gave a lecture on the dipoles, and he asked me, could you please tell this story, because it fits very nicely to what your story. You have, let's say, polarized, just to fermionic dipoles. Single component. So here, although we have single component, and we think about kind of P wave or whatever collisions, because it's a dipole interaction, we also have non-zero P wave. You cannot ignore P wave collisions. Moreover, collisions in this case, so this, remember this, what is V dipole of R was what it is, D squared, and then 1 minus 3 cos theta between D and R divided by R to the third power. Yeah? So we have this 1 and a second D and D, which are polarized, let's say in the Z direction. And this is R in between. And this is theta between D and R. First of all, this is, of course, long range. Joko explained you this. And it's not isotropic. So it mixes all the scattering channels. So if you send the scattering wave 0, this is second Legendre polynomial. In the end, you get scattering wave if L equals 2. Yeah? If you send scattering wave 1, in the end, you get scattering momenta 1 and 3. So that mixes all odd and all even. Yeah? So you cannot classify you cannot introduce phase shifts in a different, because L is not a good quantum number. The question is, if I now have fermions, and we know, of course, dipole-dipole interaction, if I put them like that, they start attract each other. If I put them like this, they start repel each other. So who wins? And the answer is, if you look carefully, what is a P-wave scattering? Although I said it's not respect L, but you can send P-wave, and you look at the P-wave that goes out. Not forget about L equals 3. And then you find out that for L equals 1 and M equals 0, you get an attractive scattering amplitude. Just calculate the Born. Attractive. If F plus or minus 1, this is repulsive. But if we have attractive interaction, you would expect a pairing. And indeed, that was a paper of 2002 with Jora and some Maxim Marenko and Valentin Rычkov and me. We just look at this problem, and I present you the result, which is actually quite interesting. So let me only find it. Yes, it's here. So I won't bother you with the gap equations. I just write down the answers. So you get, of course, very similar things to what we have for the short-range interaction with, of course, sound magnification. TC would be 144 epsilon Fermi, and that is nice number. 144 is definitely better than 0.28. So, and then you have here e to the minus 1 over f d. D dipoles. Yeah? Very similar structure because it's, again, kind of BCS approach. And FD is what it is. It is 12 density dipole moment squared. Sorry, I don't write this 4 pi h0 epsilon 0. So, and then here we have pi epsilon Fermi. And to give you an estimate what it means, yeah, remember Jore introduced this R star, which was md squared over h bar squared, which also very often called a dipolar scattering length, although it's not the scattering length in the usual sense that you define for isotropic interaction for the S-wave channel. Then this quantity means if you put all these things, you get 4 over pi squared dipolar length of this R star, P Fermi, divided by pi h bar. Yeah, if I put here 2 and I put here 2, yeah, you recognize that would be the analog of F for the short range interaction with just AD replaced with A, and there's some numerical coefficient. Yeah. But more interesting is the structure of the order parameter. Yeah? So order parameter in this case depends on P, it's not a constant. It depends on modulus and direction. And if I look at it at the Fermi surface, yeah, so it's on a momentum, it's relatively smooth behavior with a typical scale epsilon Fermi. So close to the Fermi, it's a rather smooth behavior. But the angles are very interesting. So what you will have delta 0 constant, and then comes this funny function. Okay, I read square root of 2, it was some normalization. Sinus of pi over 2 cosinus theta. Of course, you can expand in cosinus theta and then expand in the Legendre polynomial and see that actually here all odd L contribute. So it's actually a mixture of all odd scattering channels that are coupled by this anisotropic dipole interaction to each other. Dominant is, of course, P wave. Dominant P wave. L equals 1. This is a dominant contribution. So if you plug in what I said, here you get a small difference with a number here. Yeah? So this is kind of, you see, this is very anisotropic. And for theta equals 0, it is 0 because cosinus pi over 2, sorry, for theta equals pi over 2 in a plane perpendicular to polarization, yeah? Cosinus pi over 2 is 0, order parameter is 0. So it has this form. So here is plus, here is minus. Yeah, like what is A? What is the analog? I forgot what is the A1 for helium-3. They also have P-wave pairing, which sort of anisotropic order parameter. So it behaves like this. It's not uniform everywhere. On a Fermi surface, you have a line of zeros. That means a specific heat will get a not exponential, but power. Yeah, so it's variation. And the last story, very short. I will now confuse you. Let me now consider two-component Fermi gas with short-range repulsive interaction. Yeah? So it's exactly where we think we're sitting here. On that side of the story, it's a normal gas, and nothing happens. And this is not the case. This is not the case. And that was first discovered by Kohn and Luttinger. And it's again built on this interaction in the media. Yeah? So now we have A positive. Yeah? So you have repulsive Fermi gas. Let's now have a look closely on the interaction between plus particles, for example. Yeah? So we have plus, minus, minus. So directly, they cannot interact. Yeah? They can only interact with a P wave, which is small. Yeah? But, Yeah? Plus, plus. Yeah? They can only interact with the P wave, but this is small. Yeah? It's indeed small compared to the effect that I want to discuss. But you can have the following thing. Plus, create a particle Hall excitation in a minus component, and the second plus, read it, yeah, scatters on this excitation. Yeah? So this gives you effective interaction between plus particles, yeah? Through this polarization of the minus. And of course, minus through the polarization of the plus. It's symmetric situation. So if you calculate what it means, this one is called the Linhart function. If you look at it, so of course we will always have this P minus P prime, P prime, and this depends on cosinus theta for P equals P prime equals PF. This is the angle between. It has really dependence, and what you find out for L larger or equal 1, it's negative. L equals 0, positive. So that means in all channels, starting with P wave, D wave, F wave, you have an attractive interaction between particles, which is second order. P wave here would be third order. So for P wave, etc., this would be the dominant channel for the interaction. And as I said, it's negative, so that means you will have here P wave pairing. But Tc would be minus 1 over some coefficient, which is big one, F squared. So Tc would be extremely small, but it would be non-zero. So this looks like the pairing looks like the last chance for the nature decrease the energy. Yeah? And even if you have repulsive Fermi gas, if you go down, 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 down in the energy, you will get a paired state. But for extremely low temperature, which are unreachable, I don't know, maybe in cold gases they can reach it, but yeah. There was the idea that this mechanism was in helium-3, but helium-3, it's a strongly interacting system. You cannot say anything. So here you can only think about the asymptotics behavior, but L equals 1, it's somewhat you cannot reach with analytical tools. Numerically, people do it in a Hubbard model, weakly two-dimensional similar effects they put in a Hubbard model because it's easy to calculate. Yeah, but the low density is such that it's kind of approximation of the free gas. And they find a couple of interesting phases of these things. So I think I am finished. Yeah. So thank you for your attention and questions. Questions.
Sorry, I wonder why is it that only the odd L contributes to the?
Because.
Can you say it again?
No, here, this is because the dipole, anisotropic dipole-dipole interaction, it mixes all scattering channels, but it mixes odd with odd and even with even. The only thing that is preserved is M equals 0. M is preserved because you have a symmetry around the polarization axis. That's why here there is no phi. It's M equals 0 channel always. Now, there is no phi. It's only theta. But if you expand these things, yeah, you get odd power of cosinus. At odd powers of cosinus, if you look at a thick book, it's expressed in terms of odd power, not power, odd order Legendre polynomials. And odd order Legendre polynomials describes you odd scattering these angular harmonics. That's why. And if you calculate S wave, well, actually S wave you won't get here, because if you send S, you get L equals 2. So S you get in the second order. It's 0 S to D and D to S back. So you get effective this potential 1 over r to the 6 that corrects the van der Waals That's why you can have some special resonances when you apply electric field. Yeah. But the pairing it's in a odd channel, dominant P wave. So you can call it P wave, but actually it mixes all the channels, odd angular momentum channels due to anisotropy of a dipole-dipole interaction.
So is there any way for the reduction of the energy to be, because in this case it goes to the force?
No, this is delta. This is delta. This is delta, the order parameter. Yeah. So the Fermi surface would also be slightly deformed. Of course, this is a different story. You can also slightly deform the Fermi surface because it's an isotropic force. Particles wants to. But this is, yeah, you have to take many effects into account with dipole-dipole interaction. So, yeah. But if you want pairing, it will be look like this. It's dominantly P wave with this sort of order parameter. No topological Px plus IPy. It's this one. More questions? Okay, then we are done with this course. So thank you for your attention. And we are in time.
Okay, so we reconvene in half an hour after the coffee break.
Okay, yes. Just a second, let me just switch off these devices.